What happens to a ship when it disappears beneath the surface of the ocean? Most people imagine the same sequence. The water rises, the hull tilts, the lights go out, and then there is only darkness, pressure, and the slow, patient work of decay. We picture rust consuming steel. We picture silence swallowing the last trace of human presence. That image is understandable. It is also incomplete, because the deep ocean does not simply destroy what falls into it, it transforms it. A ship built to carry people across open water becomes something its engineers never imagined. Its corridors become passageways for fish. Its steel hull becomes a surface for microbes, coral, and creatures that have never once needed sunlight to survive. This is not an accident of nature. It is nature doing precisely what it has always done. There are roughly 3 million shipwrecks resting across the world's ocean floor. Each one, regardless of its history, eventually enters the same quiet process. The ocean receives it. And the ocean begins, slowly and methodically, to repurpose every surface, every cavity, every shadow it contains. A shipwreck does not end when it sinks. That is precisely when its second existence begins. Most deep-sea shipwrecks lie between 1,000 and 6,000 meters below the surface, in regions known as the bathyal and abyssal zones. At these depths, sunlight has long disappeared. Photosynthesis is impossible. The temperature hovers near freezing year-round, typically between 1 and 4 degrees Celsius. And the pressure reaches levels that are genuinely difficult for the human mind to comprehend. At 4,000 meters, the weight of water pressing down exceeds 400 times the atmospheric pressure we feel standing on dry land. These are not empty spaces. These are environments where entire mountain ranges exist in total darkness, where plains stretch for hundreds of kilometers without a single interruption, where sediment drifts down from the distant surface above like slow, invisible snow, settling over millions of years into landscapes older than most of what we see on land. When a ship reaches this world, it does not arrive in a void. It arrives in one of the largest ecosystems on Earth, a system covering more than 60% of our planet's surface, and one that science has only begun to understand in the last few decades. The deep sea is not empty. It never was. It is simply a world built on different rules, running on different energy, moving at a different pace than anything we experience above the waterline. And into that world, a ship descends. Down here, the natural limits define everything. Pressure compresses gases, slows chemical reactions, and alters how proteins function inside living cells. Cold temperatures reduce metabolism and push decomposition to a near standstill. Darkness removes the primary energy source that powers nearly every ecosystem we can see from the surface. Even sound behaves differently here. Light cannot travel more than a few meters before it vanishes entirely, but sound waves can carry for hundreds of kilometers through dense cold water, becoming the dominant way energy moves through this world. Corrosion behaves differently too. In oxygen-poor deep environments, steel sometimes deteriorates more slowly than it would in shallow coastal waters. But chemistry is never the whole story. On wrecks like the Titanic, deterioration is driven not only by seawater, but by specialized bacteria that consume iron itself, forming structures known as rusticles, fragile formations resembling underwater icicles that are actually living microbial colonies feeding directly on metal. Decay, down here, is not simply chemistry. It is biology. Every process that would destroy a ship on the surface is replaced, at depth, by something slower, stranger, and far more alive. The rules do not disappear. They simply transform into something the surface world would barely recognize. And in that transformation, something unexpected begins to take shape. Humans cannot exist here without technology, and even our best machines struggle. Submersibles must be engineered to withstand crushing pressure that would collapse an unprotected human body in seconds. Electronics must be sealed against relentless salt intrusion. Every light source must be artificial. Every degree of warmth must be generated from within. A single mission to these depths requires years of engineering, immense financial cost, and a tolerance for risk that few institutions are willing to accept. A human being without protection would not survive long enough to understand what was happening. Gas spaces in the body would compress almost instantly. The cold would begin its work before the pressure finished its own. Survival, in any meaningful sense, would be measured not in minutes, but in moments. And yet life exists here permanently. Not struggling, not barely holding on, but thriving, adapting, and building complex systems in conditions that would end a human life before it could draw a second breath. That distinction matters. The deep ocean is not hostile to life. It is hostile to our version of life. It is hostile to the particular biology we happen to carry, the pressure ranges we were built for, the temperatures our cells were designed to tolerate. But life itself has no such limitations. Down here, it simply found different solutions, and it found them long before we ever thought to look. Deep-sea organisms survive not by resisting this environment, but by aligning with it completely. Many species produce pressure-stable proteins that do not deform or break down under compression. Their cell membranes contain specialized lipids that remain flexible even in near-freezing temperatures, where a normal cell membrane would stiffen and fail. Some produce compounds that prevent internal ice crystal formation, protecting delicate biological machinery in conditions that would destroy most living tissue on Earth. Energy comes from sources that would seem impossible from the surface. Instead of sunlight, many deep-sea organisms depend on marine snow, a continuous slow rain of microscopic organic particles drifting down from ecosystems thousands of meters above. Others rely on chemosynthesis, where bacteria extract energy directly from chemicals like methane or hydrogen sulfide seeping through the seafloor, building entire food webs from chemistry alone rather than light. This is a world that learned to live on what falls and what leaks. And then a ship arrives. It brings something that this world rarely has, something that, on the abyssal plane, is genuinely scarce. Structure. Most of the deep sea floor is soft sediment stretching in every direction without interruption. Hard surfaces are uncommon. Vertical walls, overhangs, enclosed cavities, and complex three-dimensional geometry are rarer still. A sunken ship delivers all of it at once. To the organisms of the deep, that is not wreckage. That is opportunity. Within weeks to months, the first colonizers arrive. Mobile scavengers appear first. Amphipods, deep-sea shrimp, and rat-tail fish move in to investigate the new structure. If organic material remains aboard, hagfish and sleeper sharks follow, drawn by chemical signals traveling through water, the way scent travels through open air. Nothing that can be consumed is left unconsumed. The deep ocean does not allow waste. Bacteria are already at work before any of them arrive. Biofilms form across exposed metal surfaces within days, laying down the biochemical foundation that every organism arriving afterward will depend on. Some of these microbes metabolize iron. Others break down sulfur compounds or hydrocarbons leaking slowly from cargo holds and fuel residues still sealed inside the hull. Soon after, the suspension feeders move in. Anemones, sponges, crinoids, and cold-water corals attach themselves to the exposed surfaces and begin drawing nutrients from currents passing through the structure. They do not chase food. They position themselves where the ship's geometry forces water to move, and they let the flow deliver everything they need. Life does not arrive randomly. It arrives in sequence, each wave preparing the surface for the next, each organism making the wreck slightly more habitable than it was before. The ship is no longer simply sinking into the ocean. It is being read, claimed, and slowly rewritten by everything that lives here. Over time, the wreck becomes what marine biologists call an artificial reef. Fish begin using interior cavities for shelter, moving through corridors and compartments the way they would move through rock formations on a natural reef. Predators learn the geometry of the structure, using overhangs and blind corners as ambush points. Filter feeders position themselves along edges where currents accelerate around the hull, delivering food particles far more efficiently than the flat sediment surrounding them ever could. Studies of deep wrecks have documented something striking. Biodiversity around these structures can exceed that of the surrounding seafloor by a significant margin. Some species appear only briefly, passing through as the wreck sits along a migration corridor. Others establish permanent colonies that persist for decades, generation after generation, on a structure that was never designed to hold them. The ship stops behaving like debris. It begins behaving like geology. Its presence reshapes local water movement, alters sediment patterns, and creates a cascading series of biological opportunities that spread outward from the hull in every direction. In some documented cases, the total biomass surrounding a wreck exceeds that of nearby natural seabed areas by several times, particularly when structural complexity remains high. Complexity creates life. It always has. And a ship, with its layered decks, enclosed spaces, and vertical surfaces rising from the seafloor, delivers more complexity to this environment than almost anything else that could arrive here naturally. The geography of the deep ocean shapes everything about how these ecosystems develop. Currents determine which larvae and spores ever reach the structure in the first place. Sediment flow can bury lower decks over the course of decades, slowly erasing entire sections of the wreck from biological access. Nearby seamounts or underwater ridges influence how nutrients move through the water column, and wrecks positioned along continental slopes often experience significantly higher biological activity because of the nutrient transport flowing down from shallower zones above. Even the orientation of the wreck matters more than most people would expect. A ship resting upright on the seafloor develops different biological communities than one lying on its side. Vertical surfaces attract different species than horizontal ones. South-facing walls host different organisms than north-facing walls. The angle of current strike against the hull changes which suspension feeders can establish themselves and where. The wreck becomes something like a microcontinent, a mountain range built by human hands, now governed entirely by physics, chemistry, and the patient logic of deep-sea biology. Every surface is real estate. Every shadow is habitat. Every current deflected by the hull is an opportunity redirected towards something living. No two wrecks develop identically. Location, depth, orientation, cargo, and the specific communities of organisms present in the surrounding water all combine to produce an ecosystem as unique as the ship itself once was. Time changes everything, and in the deep ocean, time moves differently than it does on the surface. After decades, corrosion weakens structural beams from the inside out. Decks begin to collapse under their own weight. Sediment accumulates across horizontal surfaces, slowly burying what remains. Biological growth thickens into layers dense enough to alter the shape of the hull itself. Rusticles grow, fracture, and regrow in slow repeating cycles, converting steel into mineral bacterial composites that bear almost no resemblance to the metal they came from. After a century, the ship may no longer look like a ship at all. Wood components, in shallower wrecks, are consumed by specialized organisms like shipworms that bore through timber with mechanical precision. In deeper wrecks, lower oxygen levels preserve wood far longer, sometimes for centuries. Steel slowly dissolves and reconverts into new chemical forms, absorbed into the sediment and into the biology surrounding it. Yet biological activity often increases rather than decreases as this process unfolds. As structure breaks down, it creates new complexity. New cavities open where beams once held firm. New attachment surfaces appear where decks once sealed spaces shut. Collapse does not end the ecosystem. It reorganizes it. Destruction, down here, is indistinguishable from construction. The ocean does not mourn what breaks. It simply finds a new use for the pieces. For scientists, shipwrecks are far more than historical artifacts. They are controlled ecological experiments, placed on the seafloor by accident and preserved by depth, offering something that deep-sea research almost never has access to, a known starting point. Because the date of sinking is often documented with precision, researchers can study how ecosystems develop across known timeframes. They can compare a wreck that has been on the seafloor for 30 years against one that has rested there for a century, tracking how microbial communities succeed one another, how colonization timelines unfold, how corrosion rates vary across different steel compositions and different ocean chemistries. Shipwrecks also allow scientists to study deep-sea adaptation without disturbing the fragile natural reefs and hydrothermal vent communities that take thousands of years to develop. Some wrecks have become long-term monitoring sites, where researchers return year after year to measure shifts in ocean temperature, changes in water chemistry, and the slow movement of biodiversity patterns across the deep sea floor. In an environment where controlled experiments are nearly impossible to conduct, a wreck becomes something invaluable, a fixed reference point in a world that offers almost none. A laboratory that no one designed, placed by tragedy, maintained by depth, and quietly generating data about the living systems of our planet that we could not gather any other way. And so we return to the ship itself. What once carried passengers across open water now carries something else entirely. Fish move through corridors once walked by crews. Microbes feed on metal once shaped by the hands of shipbuilders. Cold water coral grows in the exact spaces where navigation instruments once stood, where engineers once made decisions, where human beings once believed they were in control of where they were going. Human purpose fades. Ocean purpose replaces it. The identity of the vessel changes in a way that no registry, no manifest, and no historical record can fully capture. It is no longer defined by the route it sailed, the cargo it carried, or the flag it flew. It is defined now by what lives within it, what feeds from it, what shelters inside it, and what has claimed it as permanent home. A ship built to cross the ocean becomes something that belongs to it, not as a ruin, not as a grave, but as a living part of a system that was here long before the ship was built and will continue long after the last trace of steel has dissolved back into the sediment. The ocean does not preserve ships the way museums do. It absorbs them, and in absorbing them, it gives them a second identity quieter than the first, invisible to most of the world, but in every biological sense, more alive than the vessel ever was while it was still sailing. Perhaps the most remarkable truth is not that ships sink. It is that nothing the ocean takes ever remains unused. Steel becomes food, walls become shelter, shadows become hunting grounds, silence becomes habitat. Every surface that once served a human purpose is reassigned, reclaimed, and rebuilt into something the original designers could never have imagined and never could have planned. The deep ocean does not remember ships the way we do. It does not register tragedy, ownership, or history. It does not mark the date of sinking or preserve the name painted on the hull. It recognizes only structure, chemistry, and energy, and whatever arrives carrying any of those three things will be put to use. In that way, every wreck becomes part of something older and larger than any human timeline. A vessel that once measured its existence in voyages now measures it in centuries. A machine built for speed and direction now exists in perfect stillness, feeding systems that move on timescales we can barely comprehend. Because in the deepest parts of this world, nothing truly disappears. It only changes roles. If you are fascinated by the hidden life growing on lost ships, the extreme biology of the abyss, and the quiet systems shaping Earth's last frontier, continue exploring these unseen worlds with Sunken Realms Deep, where we document what survives in the places humans cannot reach.